Hey, good morning, class, and welcome to another thrilling session of Algebra 1. I'm just sure you're eager to go into section 10-2, where we're going to learn how to simplify radical expressions. Um, Great stuff, simplification of radical expressions. That's our topic for today. But before we get into that, I just wanted to mention to you that I have a new technique to encourage our slackers who are trying to take shortcuts without watching the videos, uh, to encourage you guys to watch the video and to learn. There are no shortcuts in math. You may think so. You may think you can slip by just copying off a friend or um, just trying to muddle your way through with low scores. It's going to catch up with you. In fact, it is. um, I would strongly encourage you to start watching these videos, and to do that, to encourage you to watch the videos, I'm coming up with a new technique that I'm going to try today. So I have this little phrase that I created, a little saying. It's kind of a nonsense thing, doesn't make a whole lot of sense, though maybe it does if you stop and think about it. Uh, I'm going to be giving you the words of this phrase intermittently through this video. So I'll give you the first word, a little later I'll give you the second word, a little later the third word, etc., 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 until you finally have the whole phrase. When you have the whole phrase, you're to write it down uh, in your assignment. So I would encourage you to have a pad of paper nearby as you watch this video and record the words as you go so that you won't miss any of them. And this will encourage you to watch the whole video and hopefully to learn. And by the way, if you're going to watch it to get this little phrase, which by the way is going to be worth quite a few points. So if you don't do it, it's another way to ensure that you fail. So since you're going to be watching the video anyway to get this little phrase, you might as well learn the math. So take the time to pay attention, to focus. You'll need about 45 minutes. It's about a class period. And if you think that working from home allows you to not have class, think again. This is a big mistake if that's the way you're thinking. You need to take the time to watch the lectures so that you will learn the material. So class is still on, guys. So pay attention, have a pad of paper, get this phrase so that you can um, learn your math and get the points for this assignment. So without wasting any more time on that, let's go ahead and switch to our whiteboard and get started. So simplification of radical expressions, I'm going to go ahead and maximize this screen so that we have a little more space to work with. We're going to start off with a couple of rules that we use for this simplification process. To begin with, notice that if you have the square root of a, b, product of a and b, as your radicand, so a and b, the product is under the radical sign, so it's called the radicand. The square root of ab is equal to the square root of a times the square root of b. Okay? Simple, right? Square root of a times b is the square root of a times the square root of b. And as an example, maybe we could just look at something like the square root of 14. Well, let's not do 14. Let's do 18. Square root of 18. Look at that. That's equal to the square root of 9 times 2. Okay? It's not rocket science, seems pretty straightforward, which would be equal to the square root of 9 times the square root of 2, which is equal to 3 times the square root of 2. Now, 3 times the square root of 2, we normally don't say 3 times the square root of 2 because it's a little bit long to say it that way. So 3 square roots of 2 is the way we'd read that. 3 square roots of 2. 3 square roots of 2. Your first word in our little phrase is John. Write that down. So 3 square roots of 2. We would read this like 3 apples, 3 oranges, 3 square roots of 2. 3x we say is 3 times x. 3 times the square root of 2 can be read as 3 square roots of 2. That's your first rule. Let's move ahead to our second rule. How about this one? The square root of a over b is equal to the square root of a divided by the square root of b. Okay, simple enough. Square root of a over b is the square root of a divided by the square root of b. And as an example, maybe we could show something like this. How about the square root of 7 over 4? Square root of 7 over 4. Well, that would be equal to the square root of 7 divided by the square root of 4, which would be equal to the square root of 7 over 2. Square root of 7 over 2, and that would be simplified. Okay. So 2 rules here that are simple but very important. Take note of those. Your second word in your phrase is Duncan. Duncan. That's D-U-N-K-I-N. Moving ahead. How do you know if you have your radical in simplified form? How do you know your expression is simplified, your radical expression? How do you know that it's simplified? Well, simplification requires 2 things. So simplified form is going to require, number 1, that you have no fractions in the radicand. No fractions in the radicand. So the radicand, remember, that's what's under the square root sign. No fractions there. It's got to be a number that is not a fraction. Okay. Secondly, you can have no radicals in the denominator. No radicals. In the denominator. Okay, no radicals in the denominator. So those 2 things together will let you know whether you're in simplified form. If you have a fraction as your radicand, you're not. And if you have a radical in the denominator, you're not simplified. Now, a couple of a few special cases that you need to watch out for. Tell me, look at this expression. What is the square root of x squared? What is the square root of x squared? Question mark. Is it equal to x? Now you may think, well, yeah, x times x is x squared, so the square root of x squared must be x. However, it's not always true. And you may say, how can that be? How can that be? Well, watch the following. Is the square root of negative 5 times negative 5, in other words, negative 5 squared, is that equal to negative 5? What do you think? Is it equal? Well, under our radical here, our radicand, -5 times -5 is positive 25. Is that equal to -5? And the answer is no. 5 is not equal to -5. Okay? So we've got to be careful. When we have certain expressions and we go to take the square root of them, they're not always equal to what we think they're equal to. There are certain cases where it would not be true. So here are some rules that you need to remember. They're pretty simple, so take note. Our third word in our phrase is goes. G-O-E-S, goes. So here's the cases you need to pay attention to. The square root of x squared is equal to the absolute value of x. Now I want you to take note of something. The absolute value of x is x to the first power. We normally don't show the first power, but that's what it is. So notice here that this is even and this is odd. Even power and odd power. When you have an even and an odd, you have to throw absolute value signs around your simplified expression, otherwise it would not always be true. So if you have the even-odd combination, watch out. So this is even/odd. Okay? Then you need absolute value signs. How about this next one? Let's take a look at this one. The square root of x cubed. What would that look like? Square root of x cubed. What's that one equal to? Well, it turns out that it's equal to x times the square root of x. Okay? X times the square root of x. Okay? Keep that in mind. Memorize that. How about the next one here? How about the square root of x to the fourth power? It's equal to x squared, as you probably guessed. It's equal to x squared. And you may wonder, where are the absolute value signs? Well, this is even and even. Okay? So when you have an even-even combination, then you don't need the absolute value signs. Okay? So even. And then we have the next one. How about something like this? The square root of x to the sixth power is equal to the square root of x cubed times x cubed, right? X cubed times x cubed is x to the sixth. And so the square root of that is just going to be x cubed. But notice, I want you to watch something here. This is even, and this is odd. So what do you know? You got to throw your absolute value sign around there. Make sure that you do not include the negative of that, otherwise you're going to be in trouble. So you got to have your absolute value sign. Very good, very good. So now we move on to the next word in our phrase. The next word is called or a, just the letter A. Okay? The next word in our phrase. Moving right along now, I want to introduce you to something known as the conjugate. So let's write this in a different color. What is the word conjugate? And I think what I'm going to do here is to show you this by example. So let's take an example problem. We'll call this example number 1. And let's go ahead and solve this guy. 3 divided by 3 plus square root of 5. So example number 1. 3 divided by 3 plus the square root of 5. Is this in simplified form? The answer is no. Why? Because there is a radical in the denominator. Remember, simplified form, no radicals in the denominator. Okay? So what we need to do now is to multiply this by the number 1. Recall that when we want to change the form of a fraction, we can only multiply it by the number 1. Otherwise, it will no longer be the same fraction. So the number 1 in this particular situation is going to look a little different than what you normally would see it written as. It's going to be written as 3 minus the square root of 5 over itself. So 3 minus square root of 5 minus 3 minus over 3 minus the square root of 5. So why this choice for our number 1? Why? Well, the reason is that the denominator has a special form. And the sharpest of you guys out there, the sharpest of our students, I think could recognize the form. 3 plus square roots of 5 times 3 minus square roots of 5. What is that the difference of? You remember? It is the difference of 2 squares. So if you recall, we had something that looked like this. A plus b times a minus b. And what's that equal to? A squared minus b squared. A plus b times a minus b was a squared minus b squared. Now look at these two numbers here that are our a and b. A is 3, b is square root of 5. If I square 3, I get 9. If I square the square root of 5, I get 5. So the reason we've chosen this as our conjugate, and the reason we're using this method, is to eliminate the radical from the denominator. So let's go ahead and multiply, work our way through this so you can see how it comes out. So in the numerator, we're going to have 3 times 3 minus the square root of 5. But in the denominator, it's a little different. It's going to be 3 squared minus square root of 5 squared. Okay? 3 squared minus square root of 5 squared. In the numerator, it just becomes 9 minus 3 square roots of 5. But in the denominator, it's 9 minus 5. So finally, our answer is going to be equal to the following. 9 minus 3 times the square root of 5, all divided by 4. So there you have it, simplified form. 9 minus 3 square roots of 5, all over 4. So the method we used was to multiply by the conjugate over itself. And that eliminates the radical from the denominator. It's a little trick, you could say, a little method that gets the job done. So now we have simplified form because we have no radical in the denominator. So you'll be using this technique in your assignment, so pay close attention to that. Example number 2. Example number 2. Let's go on to this one here. Example number 2. Square root of 10 times the square root of 14. Well, first of all, this is equal to the square root of 10 times 14, which is equal to the square root of 2 times 5 times 2 times 7. 2 times 5 is the prime factorization of 10, and 2 times 7 is the prime factorization of 14. We often use prime factorizations because we can see all the various numbers that can be combined and then see if we have something that has a nice square root. Well, 2 times 2 is 4. So this could be written as the square root of 4 times 5 times 7. 5 doesn't have a nice principal square root, and neither does 7. They're both prime numbers, so what we can write there is 5 times 7, or 35. So breaking that down for one final step then, this becomes the square root of 4 times the square root of 35, which is simply, to end up here, it's going to be equal to 2 square roots of 35. 2 square roots of 35. There's your final simplified answer, 2 square roots of 35, simplified down from the square root of 10 times the square root of 14. Okay, pretty simple, straightforward, shouldn't be too hard. The next word in our little phrase is hummin. Hummin, H-U-M-M-I-N. H-U-M-M-I-N. Okay, our third example. Our third example is going to be the square root of 99. This one is a little bit, maybe just a little weird. It's going to be the square root of 99 a b to the 5th c squared. Okay, so you study that for a little bit. The 99, not too difficult to deal with. What are the factors of 99? Well, I suppose you could say 33 times 3, but then 33 is 3 times 11, and 3 times 3 is 9. So how about this one? 9 times 11. Okay? I'll put those in parentheses. It's a little more clear. 9 times 11 is 99. And then we have a. And b to the 5th can be written as b to the 4th times b, and then c squared. Let's break this apart now. The square root of 9 times the square root of b to the 4th times the square root of c squared times the square root of what's left, 11ab. 11ab is what's left. So what is the square root of 9? 3. What's the square root of b to the 4th? B squared. And what is the square root of c squared? You remember the square root of c squared? Here's where maybe it gets just a little tricky. You got to remember the rule. Square root of c squared was the absolute value of c, all times the square root of 11ab. So there is our simplified expression. You may wonder, is that really simplified? It looks just about as complicated. Well, in any event, this is the simplified form. The catch here was that it's the absolute value of c. That's the tricky part in this problem. So I hope that makes sense to you. We won't be doing too many like that, so hopefully you won't find it too confusing. So that's our simplified form. Let's move on to another example. Let's do the square root of 45 over 10. Square root of 45 over 10. Fourth example. 45 over 10. What's this equal to? Well, following our rule, it's the square root of 45 divided by the square root of 10. And working on down through that a little bit more. What's the square root of 45? Well, it's the square root of 9 times 5 over the square root of 2 times 5, which we can simplify a little more. That's the square root of 9 times the square root of 5 over the square root of 2 times the square root of 5. What happens to the square roots of 5? They cancel. So we're left with then square root of 9 divided by the square root of 2. Is that simplified? Is that simplified form? What do you think? And the answer is no, it's not simplified form. Why is it not? Because we have a radical in the denominator. Okay? We're not supposed to have radicals in the denominator. So how do you get rid of it? Well, here's a little trick, something similar to the conjugate trick, except it's not a conjugate. We're going to multiply this by the number 1. Okay, our number 1 is going to be something that will eliminate the square root in the denominator. I think you might almost be able to guess what it will be. We're going to multiply this expression by square root of 2 over square root of 2. For a very specific reason. The numerator now becomes 3 times the square root of 2, but the denominator is different. The denominator becomes equal to just 2, because the square root of 2 times the square root of 2 is 2. So numerator, 3 square roots of 2, denominator is just 2. 3 square roots of 2 over 2. This is our simplified form for the square root of 45 divided by 10. Next word in our phrase is for. F-O-R. For. Let's move to example number 5. Example number 5, the square root of 52. What's this one going to look like? Square root of 52. How can we break that down? Well, start off, if you don't always, you don't always see the numbers right off. So it pays to just take a methodical approach. Divide that number by 2. 2 times 26 is 52. And you take the 26 and divide that by 2. So this is the square root of 2 times 2 times 2 times what equals 26? That's correct, 13. Moving ahead. Now you can see 2 times 2 is 4. So this is the square root of 4 times 13. And then you break that apart into 2 separate radicals. Square root of 4 times the square root of 13. And of course, you know that the square root of 4 is 2. 2 square roots of 13. 2 square roots of 13. That's our simplified version of the square root of 52. Moving ahead, example number 6. Example number 6. Okay. 7 times the square root of 63, m cubed p. 7 times the square root of 63, m cubed p. All right, well, 63. What are the factors of 63? Does it have any that have nice clean square roots? Well, as a matter of fact, 63 is 9 times 7. 7 times 9, 63. So since it works out like that, we can just go ahead and break this down as 7 times this, going to be 7 times the square root of 9 times 7 m cubed p. And then we can split this up into its various components. 7 times the square root of 9 times the square root of m cubed times the square root of 7p. Why did I choose to break it up like that? Because remember the rule for the square root of x cubed? Recall that? X times the square root of x. So the square root of m cubed is going to be m times the square root of m. So we now have 7 times 3 times m times the square root of m times the square root of 7p. And finally, 7 times 3, 21, m times, and now I can bring the square root of m and the square root of 7p together again. So 21m times the square root of 7 MP. 21m times the square root of 7 MP. That's your simplified form right there. All right. Example number 7. We're ready for example number 7. And before we go on, how about the next word in our phrase? The next word in our phrase is his, H-I-S, his. So example number 7 is 5 divided by the square root of 6 plus the square root of 3. Well, this looks like we need a conjugate, doesn't it? Because we've got radicals in the denominator. So let's multiply this by the square root of 6 minus the square root of 3 over the square root of 6 minus the square root of 3. Notice the denominator will be in the form of a plus b times a minus b. Do you see the pattern? A plus b times a minus b. In the numerator, it's pretty straightforward. 5 times the square root of 6 minus the square root of 3. However, in the denominator, it's going to be a squared minus b squared. What's a squared? The square root of 6 squared. Minus the square root of b squared. Or I said minus the square root of 3 squared, excuse me. Okay. So square root of 6 squared minus square root of 3 squared. So our numerator will just be as it is. Well, we can use distributive property. 5 times the square root of 6 minus 5 times the square root of 3, all divided by square root of 6 squared is 6, square root of 3 squared is 3, and more radicals in the denominator, so our final form then will be 5 square roots of 6 minus 5 square roots of 3, all divided by 6 minus 3, which is 3. There you have it, simplified form, and That's it. Okay, that's how you get it, by using the conjugate. Multiplying by the conjugate eliminates the radical in the denominator. That's your final answer for that problem. Now, some applications. As you recall, we often like to do problems from science that make application of mathematics. So here we go. We're going to be studying electricity. Exciting, electricity. I think you should enjoy this. Example number 8. We're going to be relating 4 things here. Power, which is measured in watts. And we use P to represent power, and it's measured in watts. Okay. Then we're going to be also talking about voltage, which we represent by V, which is measured in volts. Okay. And third, we're going to be talking about current, which is represented by the letter I. It's measured in amps. Okay. And then lastly, we're going to be dealing with resistance, which is measured by the letter R, and it's measured in ohms. And ohms uses this funny symbol to represent it. Ohms are represented by this Greek letter. Okay, so here we have power, voltage, current, resistance. Now there are 2 little equations that we will use to come up with our formula that we need. Now you may be wondering, wait a minute, this isn't physics class. No, it's not physics class, but remember, short, repetitive exposures. Short, repetitive exposures. So I'm going to show you this problem. I'm not going to ask you to derive these formulas. I could ask you to solve for a variable in a formula. That would be a fair thing, but I'm not going to be asking you to reproduce all this or to remember what resistance is measured in. But remember, if you've seen it once, it's easier when you see it the second time. Short, repetitive exposures. So here we go. There's a guy that did a lot of study with electricity. His name was Mr. Ohm. Mr. Ohm. And he came up with a law called Ohm's law. Let's write this down here. Ohm's law. Now, I like to think that Mr. Ohm had a first name. Most people do, don't they? So Mr. Ohm's first name, I don't think this is true, but I just do this for my own benefit. I say that he was Virgil Ohm. Virgil Ohm. Why Virgil? Because his law, Ohm's law, is V equals IR. V equals IR. Virgil Ohm. Hey, yeah. Do you see the connection? V equals IR. VIR. Virgil Ohm. Yes. That's Ohm's law. Now, the next formula that we have is the one for power. Power equals IV. Now, you remember how to do substitution, don't you? Substitution. We have V in the first equation. We have V in the second equation. So let's take, in our second equation, let's take this right here and substitute it right there. Okay? What will we get? Well, here's what we get. We get power equals I times what we substitute, IR. I times IR. And of course, I times I is equal to I squared R. I squared R. So now we have a new formula for power that involves resistance. Very cool. By the way, how do you remember this little equation right here? How do you remember that one? If this one was Mr. Virgil Ohm, how about the second one? This is the way I remember. I say that when you need some power, you get a IV. If you're down and out, maybe you're injured, you're sick, you need some extra power, you get an IV. Haha, joke. What, you're not laughing? You should be laughing. All right, so now we have power equals I squared R. And let's solve I squared R. Power equals I squared R. Let's solve that for the letter I. Let's solve it for the letter I. Oh yes, our next word in our phrase, pumpkin. Pumpkin, yeah, just like from the garden. Pumpkin, P-U-M-P-K-I-N. P-U-M-P-K-I-N, pumpkin. It's our next word. All right, let's solve this thing for R. Here we go. Or solve it for I, excuse me. I squared is equal to power divided by resistance. We just use basic algebra, divide both sides by R. You divide both sides by R, you're left with I squared. And then, of course, how do you get I? You take the square root. Now notice we're dealing with principal square roots. We're not dealing with negatives here. So this will be, because current is positive, you don't have negative current, right? So I is equal to the square root of P divided by R. Isn't that interesting? If you take watts and you divide by ohms and you take the square root of that, you get current in amps. Believe it or not, it works. So here we've done our first job. We've solved I. We solved for I in our equation I squared equals P over R. Now, let's give some numbers. What if you have a light bulb? Well, maybe this isn't a good example, but let's say you have just some load that has a power rating of 75 watts. 75 watts. And we're going to have a resistance of this load being equal to 5 ohms. 5 ohms. What is the current that will be flowing through the wire that's powering this electrical load? So I don't know what would have a power rating of 75 watts. Certain light bulbs are marked as 75 watts. I don't know if their resistance is 5 ohms. Maybe. It's possible. 5 ohms is a fairly low resistance, so should draw a fairly good sized current. Let's see what it would be equal to. What is 75 divided by 5? 75 divided by 5 would be equal to 15, isn't it? I don't know how you do problems like that, but I did it like this. I said 75 divided by 10 would be 7.5, and then 75 divided by half of 10 would be twice that much, or 15. Perhaps you know your multiplication tables up through 15. If you do, good for you. So this is the square root of 15, which comes out to be the number 3.87. 3.87 amps. Okay, 3.87 amps. That's the current that this load would draw. So you may wonder, what's the practical application of this? Well, you know, if you're going to have a fuse that's protecting something like this 75-watt load, you want to protect it with a fuse. The fuse should be a little bigger than 3.87, but not by too much, because maybe 5 amps or something like that. A 5-amp fuse would not blow until you drew more than 5 amps. And 3.87 is a little less than 5. If something shorted out, the current presumably would shoot quite a bit above 5. The fuse would blow and you would protect your 75-watt load. You wouldn't burn it out. Maybe it's a little radio, maybe it's some little gadget you have, whatever. It would not burn because the fuse would protect it. So there you go. Also, how big of a wire would you need to run to power that thing? Little wires can't carry much current. If you ever notice, extension cords usually are a bit fat because they have to carry current over a long distance. And the larger the wire, the more current it can carry. So knowing that you're only going to need 3.87 amps will allow you to choose a conductor, an electrical conductor, i.e. a wire, that's the appropriate size. So there you go, practical application. Practical application. Moving ahead now to example number is this number 9? I think I skipped one. Yeah, I skipped an example. Oh well, I think I won't worry with that one. Let's just go ahead to our last example, example number 9. And by the way, we need another word, don't we? All, A-L-L is our next word. All, A-L-L. That's our next word. So now we're going to do an example that is a cube root. This is one I didn't mention in the beginning of the lecture, but what would you do if you had a cube root like this? Cube root of 40. A cube root of 40. Remember that square roots could have a little 2 written right there. The square root could have a little 2 written there. But because square roots are very common and we write them very frequently, we just don't put the 2, and we understand that it is the square root, the second root that we are calculating or finding. But for other roots, we indicate which root it is. So you see the 3 here on our example number 9. The 3 represents the third root, or the cube root. Cube root. Why do you think it's called cube? Because length times width times height, yeah? Volume, cube, cubic, get it? All right, so this is the cube root of 40. So how can we write the cube root of 40? How can we simplify this down a little bit? Well, first off, we're going to look at the prime factorization of 40. 40 is 2 times 20. And that, in turn, is the cube root of 2 times 2 times 10. And that, in turn, is equal to the cube root of 2 times 2 times 2 times 5. You see 3 factors there? 3 factors. Those 3 factors are a combination that has a cube root of 2. So let's go ahead and write that out. This would then simplify down to the square root, or sorry, the cube root of 2 cubed times 5, which in the end is just simplified to the following. The cube root of, oh, excuse me, I jumped ahead of myself here. The this is going to be equal to the cube root of 2 cubed times the cube root of 5. Notice that the other roots behave in the same way. You can split them apart like that. So this is the cube root of 2 cubed times the cube root of 5. Cube root of 2 cubed is just 2 times the cube root of 5. 2 times the cube root of 5, and that doesn't look too good. Let's write this a little better. Two times the cube root of 5. That's our simplified expression. Now you need another word. Now I forgot which one. I think I gave you the word all. Yeah, I think I already gave you. Anyway, then if I already gave you the word all, I forgot. I forgot to mark it off. I think I gave you the word all. So the next one is for, F-O-R, and the last word is lovin', L-O-V-I-N. So the last 3 words are all for lovin', all for lovin', L-O-V-I-N, okay, all for lovin'. Well, that completes the little phrase, and that completes the examples that I wanted to share with you today. So I hope that you'll be able to do the assignment without difficulty. I trust it'll go well for you. This is kind of cool stuff that I think kind of like little puzzles that you can work on. So, hey guys, I hope you have a good day. I know it's Wednesday. We didn't have an assignment yesterday. I didn't even give you a lecture, so don't complain that I'm giving you something today that you can begin thinking about for tomorrow. The assignment will not be due tonight, though. It'll be due tomorrow. So I would encourage you, though, to use this day to, catch up a little bit, and you might as well get ahead. If you got a little extra time, get ahead. So best wishes to you all. Do your best, and may this next section go well for you. Study hard. Some of you really need to. All right, take care.